the situation, and how do I connect this mechanism, this event which is happening in the laboratory, or if I am doing some theory class, then in what way I think, in what way I can invent new kinds of presentation, new kinds of examples. Okay, so let me ask you a question. Fine, I see with 50 minutes are given to me, so I have so I have to do a lot of things. So this much time is not given in very little time. Okay, you suppose this is a coil. Okay, you assume this is a coil, right? It's not a uniform cylindrical coil. It's a conical, but nevertheless that doesn't matter. And suppose this is the magnet. Okay, and then you know that if the coil is stationary and the magnet moves into the coil, comes out, moves into the coil, comes out, what happens?
Flux will generate.
Flux changes. How do you know flux changes? What do you see? What do you see? Do you see EMF? What do you see? Movement.
There is a deflection in the
Good, good. You connect it to the galvanizer circuit is complete, then you see a deflection in the galvanometer, and then you start inferring things. Okay, the current has been produced, and because of this motion, the current has been produced, right? Right? Now then, how do the electrons, free electrons, they come to know that there is a flux change, and we should move. We should create a current. The free electrons are there. It's a conducting coil. The random thermal motion is there, but that doesn't make any difference. So you can assume that for this discussion, initially these free electrons are at rest. Right? Is a bad assumption or a good assumption? It's a bad assumption. But the writer is there for this discussion, for this current discussion. Even if I have just a wire, all the free electrons are free, so they can go anywhere with different velocities, different speeds, different directions, and then getting scattered from this defect and that ion and here and there. But the current is zero, the applied voltage is zero. There is no drift velocity, right? There is no drift velocity. There is no current. What is the relation between drift velocity and the current? Current density. So if the current density is not there, the current is not there. What is not there? NEV. N is there or is not there? Is there. That is not going to reduce. E V V is zero. That V is zero. J is N into E into V. If there is no current, then that V is zero. We are talking about that V. The thermal motion is still there. The free electrons are still moving. And what kind of speed, if I calculate classically, although the electrons in a metal is not a classical system. It's a huge quantum system. You have to see all band gaps and conduction band and valence band and the separation between the bands and so on and so forth. But if I think just classically to get some idea, what kind of speed do you think the thermal motion of the free electrons?
10^5.
I don't know. Whatever you say is okay with me. Just it came to my mind. We should have these numbers also to get a feel that okay, this is the kind of wrong geometrical picture that I am containing in my mind about the electrons in a metal. But still, it helps. It helps. Still, it helps. Okay, so barring that thermal motion, which has no role in production in current. Right? So as far as the production of current is concerned, when the magnet moves in the coil, we can take that these things are at rest. Fine? Because a systematic velocity is not created. It's random phenomenon. Alright. So the electrons have started moving. When I say started moving means in a systematic manner, in a particular direction, so that there is a current and the galvanometer shows it. Right? So how does an electron which was at rest started moving? How come it came to know that there is some flux change through the coil and now we are all asked to move in that systematic manner? Huh? Think of a free electron here in the coil. Why did it started moving? Because of magnetic field. Okay. Now this charge, this particle, this electron was at rest. Thermal motion has no role, and there is no systematic motion. Okay. If someone is going that way, someone also going that way, that will not create current. But you are seeing a current. You are seeing a current, right? And thermal motion is not producing any current. Systematic motion is producing current. So we are talking only in terms of the systematic motion. So in that definition of motion for this particular problem, the electron was at rest, the magnetic field was there. And if you want to consider thermal motion, I am not shying away, but then I will say that if some electron is going because of the magnetic force and velocity, thermal velocity in this direction, the other one is going that direction, the other one is going that direction. Here all the electrons have started moving in one particular way to give you a current. How come that happened, and how the electrons now know that we have to move in a correlated manner, in a systematic manner, in a one particular sense? How do all the electrons know about it?
Is it Lorentz force?
Lorentz force, yeah. So that's what came from here. Lorentz force is your magnetic use a magnetic field. Now that thermal motion will not have any contribution to that, and the systematic motion. Think of that. You can take all the things are at rest as far as this current production is concerned. So an electron at rest, will it feel Lorentz magnetic force Q V cross B? So the magnetic field is not making it move. Then what makes it move?
Relative motion?
Motion doesn't is not the cause of motion. Huh? This word is very important. Relative motion. Tell me, which motion is not relative? Which motion in the universe is not relative? When I say an object is moving, something, boat is there in the river, or moon moves, or this moves, or that moves, this is not moving, that is not moving, and this is moving, my hand is moving. Can you think of discussion of motion without having some frame in mind relative to which the distances are changing? Without this, because your velocity is distance covered divided by time. So you have to measure the distance, how much distance is covered. Right? So it's relative to something. This tumbler, this lid here, this water here, this flower bouquet here, they are at rest. They are at rest. But are they not moving relative to the sun? Are they not taking part in that 365 days completing the orbit? Is it at rest? No. So when you say that it is at rest, you are talking of relative to this room. Relative to this room. When you say that the moon takes 28.3 days to go around the earth, then you are not talking relative to, you are talking to relative to something else. Any motion you think of, any time, whenever there is a zikr hota hai jab, when you talk about velocity, motion, rest, it is always relative to something. So somehow this relative velocity word is not fitting in our scheme. There is nothing like special, nothing special about relative velocity. All velocities are. My question is still there. The electron was very happy sitting here. At some t equal to 0, he got a signal start moving. What made it move? The magnetic change. How does the electron know about the change in flux of the whole coil? The electron is sitting here. It's part of the coil, okay. But this electron, which is sitting here, how does this know that there is a magnetic field? It is at rest. So it will not identify magnetic field. And we are thinking that it knows that there is a magnetic field. It knows that there is an area. It knows that there is a flux. B dot dA integral, and then it knows that as a function of time that flux has started changing now, and therefore I should move. How does the electron know that? Okay, let's come to electromagnetic force. Okay, electromotive force. This is a wire. This is a wire. Okay, I connect it to a battery. Just 1.5 volts battery, this end, that and I connect it here. And the electron is sitting here. How does this electron know that the battery has been connected? I should move in this direction. Okay. Okay. Let's discuss that now. Attraction. Here is an electron. It is attracted by something. So that must have a positive charge. So here is that electrode or a battery or something. So there has to be attracted means there is a positive charge here. So let's come down simpler situation. There are two charges. There are two charges, Q1 and Q2. How does this Q1 know?
Forces at a distance.
How does this Q1 know that a second positive charge is brought and put at a distance from field? Okay? This charge creates some kind of a field. And this electron only knows the field and nothing else. So at the site of electron, after 14 minutes, at the site of electron is a field. Electron can only talk to that field. Right? Electron can only talk to something which is there at that site. The role of this positive charge is to create a field there. And once the field is created there, that will attract it. Okay, now come back to our coil. Here is that electron. So why did it start moving?
Changing magnetic field produces electric field.
Electric field.
That attracts the electrons.
And therefore the force was exerted by the electric field. Okay? It did not move because of flux change. It did not move because of EMF. Those are higher order reasons of this. The immediate why this electron started moving is the force exerted on the electron. And the force is exerted by electric field. And electric field was produced here because of changing magnetic field, not changing in magnetic field. Changing. Keep changing. As long as it's changing, it can produce electric field. right? So once I am moving this magnet, this moving magnet is creating electric field. Electric field can be created by charges which are kept here, kept there, and also by changing magnetic fields. And this magnet is creating changing magnetic field first. That changing magnetic field is creating electric field. That electric field exerts force on this. Alright? So the mechanism of this galvanometer deflection is the electric field produced by this. Now, the second part of the experiment. The magnet is stationary and you have coil. And the coil is moving. Right? The coil is moving. And you again see a deflection in the galvanometer. The magnet was stationary. The magnetic field was not changing with time. What made this electron to move? What made this electron to move in that systematic manner to create a deflection in the galvanometer? What exerted force on it?
There is a relative motion.
What is relative force? There is no relative.
With respect to magnet here.
No. See, I am entitled, right? I am entitled, I have gotten the certificate, to use a valid inertial frame. And whatever inertial frame I want to choose, I can choose. I have the right to do that. And stick to that inertial frame. So I am talking everything from this hall, from this classroom, from this lab, right, with respect to this room. This is an inertial frame. All my sentences will be with reference to this. You are saying that there is a motion of this electron, this magnet, even if the coil is moving in the room frame, the magnet is moving in the coil frame. So you are asking me to go to the coil frame in which the magnet is moving, and that first part of the discussion will be valid. Number one, why should I go to other frame? This is a very good inertial frame. Number two, this coil frame is not an inertial frame. Why? No, it has acceleration. So not only you are asking me to go to some other frame, you are asking me to go to a bad frame. Not even a bad frame, where all these laws are under suspicion. All these laws, Maxwell's laws, are not valid for non-inertial frames. Okay? Why should I go to that frame? So I will stick to it. The magnet is not moving. I am talking of this room's frame. The magnet is not moving. It's the coil which is moving. And if the magnet is not moving, the magnetic field is not changing anywhere. The electric field is not produced anywhere, and it is not produced here also. So how do the electrons know that we should move to deflect the galvanometer? And I am putting the magnet here. Is there an electric field? No. But there is no electric field. There is no electric field in the room. In this room, there is no electric field. Correct? There is a magnetic field. In the North Pole, South Pole, so you have magnetic field in the room, but no electric field in the room. So now I bring a coil and I move it. In a room where no electric field is there. And don't ask me to go to the coil frame. In the room's frame, there is no electric field. I brought a coil here and started moving it.
Yes.
So should it experience an electric field now? No. There is no electric field. In the room there is no electric field. Neither here there is an electric field, nor there is an electric field. Okay? There is zero electric field anywhere. Everywhere. Zero electric field. So even I put a coil here or here or here or here, I am moving. There's no electric field. Still the electrons have started moving. So what made it move?
V cross P's.
Sir? Sir? Sir. Huh?
Velocity is changing.
This time velocity is changing. Okay. Okay. This time velocity is changing. I can move this coil with a uniform velocity also. Then also the galvanometer will deflect. Suppose I move this coil with a uniform velocity. Huh? Okay. Will there be a deflection in the galvanometer? Or I need an acceleration of this coil to create a this thing there.
Acceleration.
I need acceleration. Okay. Let me say that my coil is short, not this big. Few turns. Right? Few turns. 10 turns. Here's the magnet. And this coil, only this coil, is coming with a uniform velocity, continues with a uniform velocity and crosses this magnet. Will there be a deflection in the galvanometer?
No.
Okay. If I have a coil, stationary coil, and I have a magnet, and I take this magnet through this coil with uniform velocity from this side to this side I have taken, will there be a current in this?
No.
No. You perform this experiment and then see what happens. And then go ahead. Huh? Okay, when you teach this Faraday's experiment, do you add that the coil should move with a non-uniform velocity to create this current? Do you add that part?
Yes.
Do you add?
No. Acceleration. Because only then there will be time changing flux.
Pardon?
Only then there will be time changing flux.
Okay. The coil is here
Yes.
at a certain instant. Okay? Some flux is there, it is creating magnetic field, and here is the area. So some V dot dA, right? This coil is moving with uniform velocity. Now after dt time it has come here. Do you think the flux is same V into area?
No.
It has come closer to the magnet. It's moving with uniform velocity. But at certain time t it is here, at t plus dt it is here. Did the flux change?
Yes.
Because the magnetic field has changed from x, not as a function of time. The electric field is not produced. Electric field is produced when magnetic field changes with time, dB dt. Here it is dB dx. It's a non-uniform magnetic field. So when the coil is here, there's some magnetic field. When the coil is here, there's some other magnetic field. This flux has changed. Okay? So there will be a current, even if it is moving with uniform velocity. Right? Now the same story. The same story. If there is no electric field on the electron, what made it move this way? What else can create force on the electron? The electric field is zero. What else can exert force on the electron apart from the electric field?
Another.
Delta B? Delta B by delta T is zero everywhere. My magnet is not moving. Everywhere, at any point in the space, dB dt is zero. You see the magnetic field here, and you see the magnetic field after time delta t. There is no electric field anywhere. There is no dB dt anywhere. B is everywhere. dB dx is there. dBdx is there, but dBdx does not produce force on the electron. The electron doesn't know how it is uniform or non-uniform. Whatever is at the site of the electron only knows that. If electric field is zero, what else can exert force on the electron?
So magnetic field is changing there or not? Magnetic field is changing there.
No, it's changing not with time. Okay, not with time. I am talking a particular time, a particular instant. It's moving, but a particular instant it is at one position, although it has a velocity. At that instant, the electron is experiencing a force. Electron can experience a force if there is an electric field, and if there's no electric field, is there something else which can exert force on the electron?
Only magnetic field is there, I can create it.
Only the magnetic field is there.
That's the only possible reason and how I.
Apart from gravitation, etc., which has no law, you have QE and QB cross B. A magnetic field can create force on the electron, moving electron. Okay? A magnetic field does create force on a charge, and it is given by QV cross B, where V is the velocity of the charge at that instant. I am talking from the inertial frame of this rope. My magnet is at rest. This whole coil is moving this way. All the free electrons are tied to the coil. The whole coil is moving in a systematic manner in this direction. So all these free electrons are also moving in this direction. And there is a magnetic field out there. So there's a possibility of Q, V cross B. There's no possibility of Q capital E. There's no capital E. There's no dBdt. And I'm not using any dBdx. Okay? The force is not QV cross dBdx. But there is a magnetic field at this instant. At this instant, there is a magnetic field here. After some time, the coil will reach there and it will experience this new magnetic field here, which is same as it was earlier and it will be in future, but the coil has reached there to experience that. But that is not creating any electric field or any force. There is a magnetic field, there is a Q, there is a V. Okay, now tell me another question. Here is the magnet, this is the North Pole. Okay, this is the North Pole and this is the South Pole. What is the direction of field here? Magnetic field, because of this magnet. What is the direction of magnetic field here? Right? Correct? And if it is this way? And what is the direction of motion of this coil? Okay. So the magnetic field of this magnet is along this line, and the electrons here, the coil here, they are moving along this line. Will there be a V cross B?
No. Parallel. Cross product 0.
So even the magnetic field is. What else? What else? The electric field is not there, so no question. The magnetic field is there, so possibility is very much there. But people have said that the force is Q, V cross B. And mathematicians have said that cross product of two parallel vectors is 0. And we understand that if this is North Pole, this is South Pole, the magnetic field is in this direction. And if I invert, the magnetic field is in this direction. In both cases, this field and this velocity of this coil. Now what happened?
Off axis points will have a cloud field.
What happened? What exactly what's on the electron?
Another electron is equal to
You are trying to help them, and then they want to do it themselves. They are not taking help from you. Is this coil is this free electron? When I say that the free electron is moving, is the free electron on this line? No. The coil is this way. The axis of the coil is in this direction. The electron is here. So it will experience the magnetic field which is here, not at the axis of the coil. There is nothing on the axis of the coil. Empty space. The electron is here, the electron is here, the electron is here. The turns are like this. And here the direction of magnetic field because of this magnet at this point, which direction it will be?
along
Some direction. Because the field lines go this way, from if this is North Pole, then it goes this way. One central one goes straight, which will not interact with that electron. But the one which can reach there at the site of the electron will feel only the things which are at the site of the electron. Okay? So here the magnetic field line which reaches here will go here, then make a turn and then come back, right? So wherever the electron, the magnetic field is not going to be the parallel to the axis. It will have some angle. So you have V cross Q, V cross V. It is the magnetic field which drives the current. Right? So if I move the magnet, the electric field produced by this moving magnet will drive the current. If I keep this stationary and move the coil, everything from the room frame, then it's not the electric field, the magnetic field which is driving the current. Mechanisms are very different, but the current in the galvanometer is exactly the same if these velocities are equal, or you just change your frame, because it's difficult to move the coil with the same velocity with which the magnet was moving at an earlier time, matching all the geometrical conditions. The same phenomena you see from the room frame and some other frame. And then you can see in one frame you don't have electric field, other frame you have electric field that drives the current, so on and so forth. But the result is exactly the same. And this puzzled Einstein. Then mechanisms are so different. In one case, is the moving magnet creating electric field resulting force QE, and then the current is created. And in the other case, there is no electric field, the electrons are moving, and then it is QV cross with totally different equation, totally different mechanism, and then that produces current. The currents are same at the end of the day. And from there resulted what? Which theory? Which theory?
electron.
Electron theory?
Electromagnetic.
Band theory?
Electromagnetic.
Electromagnetic theory, okay. Electromagnetic theory was formulated by Maxwell.
Maxwell, yes.
Maxwell's equations. And that was much before Einstein.
Special theory of physics.
Special theory of relativity. If you read that 1905 paper,
Yeah.
the title is On the Electrodynamics of Moving Charges. It doesn't talk of some mechanical motion and this that. That comes in the text. But the title is On the Electrodynamics of Moving Charges. And the introduction paragraph exactly tells what I am telling you now. Right? He refers to this experiment. And then he says that if the magnet is moving, this is the mechanism. And if coil is moving, totally different mechanism. It cannot be a coincidence that the two are giving me the same current. So there has to be some deeper significance. From there it starts, and the entire special theory of relativity is formulated based on it. So this Faraday experiment is a very historically very important, not only in terms of our tube lights and our fans, but also in terms of our GPS. You go anywhere, I'm coming from Kuppam, so all the time the driver was looking at that GPS, the direction this side, that side. So it all started with this Faraday's experiment. The special theory of relativity resulted from that, and that brought Einstein to think deeper. And then the general theory of relativity came, and then all this GPS, etc., these things are working based on these theories only. Right? So, sir, time है ना?